Hello and welcome back. We have been discussing the pedagogy of the course and we have just discussed how many lectures we are going to uh, spend on each topic, and now I want to take a quick tour through the material and make comments about how to teach different topics. The first topic is how to begin. So I think it is really important, if possible, to begin with a bang and somehow get to the essence of programming on the first day. Because as we argued earlier, if you do that, you will get your students excited, you will get your students motivated, and that motivation and that excitement will stay through the course. So I recommend an introduction using turtle geometry. So this turtle geometry was invented in the 1960s by Seymour Papert as a part of the Logo programming language. I should say Seymour Papert and his collaborators. And this was for teaching programming to children. Okay. So a turtle in turtle geometry is a symbolic animal that lives on the screen. Okay. And it moves as per the commands given by the program. It has a pen which draws on the screen as the turtle moves. And the goal of turtle graphics is to draw interesting pictures on the screen. Okay? Not compute, but draw interesting pictures. You will see why that is not an easy undertaking, but yet you can already guess that it should excite young children. So let me begin by showing you a simple program fragment. The Hello World program, if you will, of Turtle graphics. So the first statement in this program, Turtle Sim, is a statement which causes the computer to start up Turtle graphics. So this will create a window on the screen, okay? The window in which the graphics will happen. Once this happens, you will see a small red triangle come up, and that triangle will symbolically represent the turtle. Forward 100 is the next statement, and this statement tells the turtle to move forward 100 pixels. Right 90 tells the turtle to turn right by 90 degrees. While explaining this, you could say that instead of right 90, if I write right 45, the turtle will turn by 45 degrees. So you get to tell the turtle how much to turn. So the next is forward 100 again. After that, it is right 90 again, forward 100, right 90, forward 100. So let's pause for a second. You can tell your students and try to think of what picture the turtle has drawn. Well, let's try that. So suppose this is our turtle and it is pointing in this direction, and the first command it sees is forward 100. So it moves forward 100 pixels. After that, the next command it gets is right 90. So it turns right 90 degrees. Then it moves forward 100 pixels again turns right 90 degrees, again moves 100 pixels, again turns right 90 degrees, and again moves forward 100 pixels. What has it done? Well, clearly it has drawn a square. Okay? So this is how you draw a square. And you can expect students to understand this very fast, and if you show them the program and execute the program for them, as we will in a minute, you will see that the students learn right away. So you ask the students what this draws. Okay. So this gives our first program. Well, the first program actually is a little bit more complicated because there are additional things in it. So there are these waiting statements. Okay. So you have to make the turtle wait, because otherwise the whole thing will happen so fast that you will not get a chance to see it. And then you need that line simple CPP because you want to tell the computer that, look, I want to use the graphics functionality. Now, all of us teachers know that when we write a C++ or C program, we need some preamble. And for example, in C++, it is customary to include the header file IOStream and also say maybe that we are using the std namespace. Now, this is very difficult to explain to the students on the first day. So, we are going to do this inclusion as a part of that include simple CPP itself. So, we can spare these gory details to the student on the very first day. Main program is also a preprocessor macro, just as we talked about the preprocessor macro repeat. Now, this gets translated into int main, and again the motivation for this is that int main open parenthesis close parenthesis is really complicated to explain on the first day. So, instead of that, let us hide it and we will explain about int main when we talk about functions. So, I mean this is a detail, this is an uninteresting detail right now. So, let us not clutter up our teaching with these uninteresting details. Okay. So, yes, students must understand namespaces, IOStreams, int main, but they do not have to understand it on the first day. Okay. So, let us stop over here. Oh yeah, by the way, the weight is going to be put there so that students have time to see what the turtle is doing. Okay, so now I am going to use my computer and I am going to show you how to compile and execute that program. So, I have an editor called Emacs which I am going to use, but you could have used any other editor as well. So, in my Emacs editor, I have already typed in this program. So, as you saw, I had written include simple CPP, turtle sim and all of that. Let me increase the fonts a little bit. Okay. Yeah. So, I have this program, you can see I have put in weight 0.5 after forward and right, so that the turtle waits, and at the end I have put in a wait of 5 seconds. So, this program we typed, we saved it, and now we are going to compile. So, the compiler script is S++ instead of G++, and now I am going to say S++ file name, so square.cpp. So, it is now compiled. As you can see, when I use S++, it actually calls the G++ compiler with various options. So, the student does not need to know the options, but they are being shown here just in case somebody is curious. Now, I have to execute this. So, I can type .a.out. So, that creates this turtle, it executes that square drawing program, and then it waits for 5 seconds and disappears. Okay. All right. So, let us go back to the lecture. Okay, so this is the full day 1 program that we talked about and we just executed a minute ago. So, here is the second program for the first day. So, here I have everything except that instead of typing in forward 100 right 90 4 times, I have put them inside a repeat. So, what I do when I teach this course is I show students this program, okay, without explaining what repeat means, and I ask them to guess. What do you think this could mean? Most students understand without explanation. After all, what else could it mean? It says repeat 4. It cannot mean repeat 15 times, or repeat has to have some meaning. So, it had better mean repeat whatever follows 4 times. So, students will guess that it means repeat the sequence of command forward 100 right 90 4 times. So, this program will do pretty much the same thing as the last program, except that it is much more compact. Here is another day 1 program. So, this time we have a repeat 4 which contains forward 100 and right 90, that is inside another repeat 10. So, we are going to draw a square, that repeat 400 forward 100 right 90 is going to draw a square, and we are going to repeat it 10 times. So, are we going to draw the same square again and again? Well, no, we are going to turn right by 10 degrees. So, what is going to happen is that if we are drawing squares, we first draw one square, then we turn and then we draw a square, we first draw one square, then we draw a square at a certain angle, then we draw another square, then we draw another square, and we do this at different angles. So that is how this program is going to work. Okay. Now I show this program on my slides or on my board, and I ask the students, what do you think it does? I don't explain to them right away. Now believe me, students think about it and students explain it quite correctly. Many students do, not everyone probably, but many students know exactly what is going on. Why is that? I think that is because repeat is so intuitive. If I put one repeat inside another repeat, then students have a clue that what is inside has to be repeated as many times as the outer repeat. Okay? I explain this, of course, but only after they have a chance to figure it out, and they do figure it out. Okay? And they do work hard because they are interested. Look, what could the turtle be doing here? That's what they think. Okay? All right. So this is more or less what I talk about in the first day, because on the first day there are also maybe other things to talk about, like what is the textbook, what are the hours, where is the lab, and all of that. So there isn't that much time, but there is enough time to say all these things. So what have the students learned? Well, let's take stock. First, they have learned control flow. Well, they won't learn it on their own. You have to say that just as you read from left to right, top to bottom, a computer also executes statements top to bottom, left to right. Okay? And then they have learned that, well, it's not always top to bottom, but there can be a repeat, in which case some statements might get executed several times, and in fact there can be one repeat inside another repeat. So see what they are learning on the first day. They are learning iteration and nested iteration. So that is pretty good progress. They will learn the basic idea of syntax, spaces, indentation, and you should tell them also. But notice that the way we have structured the lesson, the focus will not be on syntax. It will not be on that you should have a space in between one word and another. Okay, but it will be like, I want to do this and I want to write the program, and my program should look good, and what is a natural way of writing that program? So a natural way of writing a program will be to put indentation. So you do explain the indentation, but the indentation is sort of natural because they are following along with the logic. Then there is something else that they also understand. They should understand, or at least they have an opportunity to understand, which is the importance of observing patterns in what is to be accomplished and expressing them using repeat. Okay? In other words, if I want to draw a 100-sided polygon, I should not be writing 100 statements, or rather I shouldn't be writing 100 forward and 100 right statements. That is just too painful. What should I do instead? I should realize that there is some repetition, there is some pattern, and I should express that pattern in my program. That is a really important idea. It is a very important activity. Recognizing patterns and expressing them in your programs is a really important activity while designing programs. I will go as far as saying that this is an essence of programming. This is an extremely important idea in writing a program. Not that you should just know what a repeat statement is, but you should know this idea that the purpose of a looping statement is to express a pattern and not have to write so many statements. So whatever patterns come up in your computation should get expressed in your program. So this is the starting point of writing programs, or rather I should say writing good programs. The last activity for day 1 is to show students a movie of what is possible using graphics. Okay? So let me do that now. Okay, so we'll talk about homeworks, but let me first show you the movie. Okay, so I'm back to my computer and I'm now going to open the movie. So let me get it running. So there is that turtle and it will start moving. In fact, it will draw that nested square pattern. Okay, so as you saw, it is turning and then drawing another square. Okay. So that is the first program that I want to show you. Okay. After that, the turtle is going to draw a pattern which you might think of as being used for decorating plates. So this is a kind of a pattern which might appear on the border of a plate. Okay. Now it turns out that this pattern can be drawn using some 10-15 lines. It just consists of 3 nested repeat statements and of course forward and right statements. So the picture of this pattern appears on the cover of the textbook and it is one of the exercises inside as well. And I have given this exercise to as one of the first few exercises, and students have spent time to get it right. So it's a nice challenge, but students take the time to do it. This is a curve called a Hilbert space filling curve. So you can see that the first curve appears in the second, this second will appear in the third, and this curve has recursive symmetry. So this is another exercise. This is recursion made pictorial. So it is a good way of understanding recursion, and that will be discussed later as well. By the way, all these effects are also being made due to using simple CPP. So here is another recursive picture that is being drawn. This recursive picture is drawing out a tree. So the code for this is also maybe 10-15 lines. Of course, there is a function, a recursive function which is being called, and you can see the turtle is drawing the code, but as it draws the code, it leaves behind copies of it. The copies are just there so that they appear like flowers or leaves. Okay, but it looks like a pretty realistic tree. Here is a tree which is again drawn using recursion. Recursion turns out to be an important idea and it can be expressed nicely. So many of these pictures can be drawn with very small amount of code. This is done using some code which comes up towards the end of the course. This is something that uses inheritance. It's a little bit complicated, but students will be able to do it if they even read the chapters on inheritance by themselves. Okay. So you may notice that the wheels are turning just the right amount. This is something that comes up early actually. So this just requires a conditional statement and a repeat is enough. And this doesn't use turtle graphics, but uses a different kind of graphics. And what it is doing, as you can see, is it is simulating a ball bouncing. So a bouncing ball is kind of a very simple representation of a mechanical system. And the point of this is to draw a nice animation, but also understand that many mechanical systems can be pictorially simulated, and that simulation is in principle can be useful. And there is something interesting going on over here. Somehow or the other, the ball is going to now retrace its path. This is the most complicated program in this demo. It consists of this simulation of aircraft. The aircraft are shown big so that you can see them, but actually the way the program is written, they don't actually intersect. In fact, if you look at it carefully, the aircraft are kept far apart from each other. especially when they are going fast. So this is meant to be a real simulation of a two-runway airport. Well, not a real simulation, sort of a quasi-real simulation. This is going to simulate our solar system, and it actually uses Newton's gravitational law and calculates forces according to that. Okay, so that's it. So these are some of the things that you should tell the student you can do if you persist through the course, and I think that will get the students excited. Okay, so we were talking about what students have learned on day one, and then we saw this demo. And so the last activity was the demo for the day, but we should also give some homeworks. So what homeworks can we give? Well, of course, we can say if you can draw a square, can you draw a polygon? But we can do more. Can you draw a two-dimensional grid? Okay, so by that I mean simply something like this. And of course, in this, the turtle will have to go over some of the lines it has already drawn. Okay? Or maybe there are commands for raising the pen and lowering the pen. So these commands can be supplied as a part of the statement of this, or they could have been discussed in the class. I think if you see the slides for the book, they are expected to be discussed in the class on the first day. Maybe you can ask or you can show them how to draw a circle, because they have learned, our students have learned in mathematics that a circle is a limit of an n-sided polygon as n tends to infinity. So how do you draw a circle? Well, you draw an n-sided polygon where n is large, as simple as that. So for practical purposes, if you draw a 100-sided polygon, on a computer, it looks just like a circle. So students will have a lot of fun drawing circles of various sizes. And actually, one of the ideas in that plate drawing was part of it were arcs of a circle which got drawn. How do you draw a 5-cornered star? Okay, by this I mean simply something like this. The star that we draw without lifting the pen. Okay. Now, in this problem as well as in that plate design problem, there is an interesting geometric principle at play, and that interesting principle is that if I start with my turtle pointing in this direction, I draw a complicated drawing, and eventually I come back and again I am pointing in this direction. So how much total turning have I done? So I have done turning equal to 360 degrees multiplied by some integer. So just alert your students of this fact, and then they will be able to reason out everything else. So they will see that, look, I am in the star, I am going to turn by 2 times 360, and over the entire drawing I am turning 5 times. So then my turning angle should be what? 720 divided by 5. So all these things require some high school geometry, okay? But most programming needs some domain knowledge. Programming is not something to be done by itself. It has to be, we write a program about something, about some subject, and that subject has to be understood by us. Now here, geometry is something that students have learned through high school and also through junior college, and therefore they know that. And of course, let us not assume or let us not scold our students if they don't know it, but let's just be gentle and let's remind them a little bit. But yes, they already know most of it, and so we will have to do only a small amount of reminding. But the point is that this is something that they need to understand. Whenever they write a program, it's going to be about a domain, and they need to have that domain knowledge. So we need to remind them of the important ideas, and this can be done as a part of the homework statement. So what I said a minute ago, that it has to have turned a multiple of 360 degrees, could be given as a part of the homework statement. Okay. So it will help in drawing stars, it will help in drawing that plate design that I showed. Okay. And how do you draw a circle? Well, you change the angle only gradually. Now, my experience is that students are very happy to do these homeworks because they want to see, is the turtle really going to move the way I think or the way I want it to move? Okay? And basically, now you have put the students in a position of power, and everybody loves power, and they are going to want to make the turtle dance up to their tune. Okay, so now the next topic is going to be how computers solve problems. So we will discuss this. This is another part of the introductory first few lectures. We will discuss this in the next sub lecture. So we will take a break. Thank you.